So, not going to do a big recap. The small recap for previous lectures is basically we looked at the turbo decoder, okay, and before that we saw the turbo code. And the thing that I want to emphasize is some kind of a generic rule about these modern codes, okay. So called modern codes and decoders, they follow certain generic construction principles. You can't say that these are very precise from a theoretical point of view, but there are some generic principles which are used in the design of these codes and the decoders, okay, and they go hand in hand. And the goal, or what these codes have managed to achieve, which was not possible before, was low BERs and FERs, okay, close to capacity. Okay. So, that is capacity in what channel, I should tell you in what channel. In fact, for almost any channel that you can think about, any reasonable practical channel, people have been able to get very low BERs and FERs quite close to capacity. And when I say low, well, low BER is 10 power minus 6 or lower, and low FER is 10 power minus 3 and lower. Okay. So, that is what these codes have accomplished. And what are the major guiding principles on the code design side? In fact, the principles are very generic and ad hoc. I mean, what is the main idea? What are the main ideas? Any themes? Okay. Yeah. Okay. So, it looks like okay. So, there is the idea of randomness in the encoder is quite important. Okay, some kind of randomness in encoder, okay, and this should basically make finding low weight code words difficult. Okay, so these are again, like I said, there is no major theoretical impact here, but just principles that you use, rules of thumb that you use in the design. Okay, finding low weight code words should be hard. Okay, so that should be there, and there should be some randomness which makes sure that you do this. And the other point of randomness is when you vary the randomness here. Okay, so of course there's various possibilities. That's why it's called random. It's not one possibility. You should be able to address a lot of codes. Okay, so there should be many codes that belong to an ensemble, and you should be working with one average member from the ensemble. Okay, so that seems to be like a theme here. Okay, but then you can't just make the entire code random. Okay, if you make everything random, of course the code will be good, and of course finding low weight code words is hard. Okay, if you take a random parity check matrix, finding low weight code words is hard. We saw that in the beginning also, right? Given a parity check matrix, it's hard to find low weight code words. But then what is the problem with those codes? Optimal decoders are tough. Okay, so the main impact here is you can do suboptimal soft decoding. Soft decoding must be possible. Okay, the soft is important. Okay, and how is this made possible in your encoder? This is through these ideas of concatenation and decomposition. So the main, okay, so the question is why are these message passing decoders suboptimal? Well, the independence assumption is the crucial property which is violated. Okay, so if you don't violate the independence property at any point in your message passing, then there is no problem, you will get to the optimal decoder. Okay, in fact, you can prove that, it's no problem. But the point is you will violate the independence assumption. So there is an independence assumption when you do the decoding, and that is violated. Okay, all right. So suboptimal soft decoding. So the encoder should facilitate the suboptimal soft decoding by making possible, by using either concatenation or some kind of decomposition should be possible. Okay, so in the LDPC codes, for instance, this there is some, okay, so let me put decomposition in code. So what I mean by decomposition is there should be a part of the code word which is decodable by an optimal soft decoder, okay. There should be a part of the code word and that part can be anything, I mean as long as there is a sub code word, so to speak, it is a long code word which you can't directly optimally decode, but some part of it should be optimally decodable, right. Once you have that, then you are enabling this decomposition in your encoder, okay. So when you do that, then you have to do message passing, right. So this involves message passing, and the important principle in message passing is, yeah, you should pass only extrinsic information, okay, and you cannot make sure that it is extrinsic globally, no, I mean that was the question that was asked about the stage of the decoding also. So you have to make sure that it is extrinsic locally, no. Locally for one component decoder, in one part of it, what it receives should not be sent back to the same part in the other decoder, okay. So you make sure that locally there is some extrinsic thing maintained, globally you do not care, okay. If you want to care about global extrinsic and all that, then you have to take care of the entire MAP decoding, and then you will be again stuck with the difficulty of optimal decoding, okay. So your problem will become very very difficult, okay. So hopefully this local thing is clear to you, okay. So when what you do in your message passing in LDPC codes, for instance, you make sure you pass extrinsic information from each check node only, that is all, okay. But if you do the ultimate tree, the decoding tree, right, you remember I drew a decoding tree, there might be repetitions at some levels, okay. Once you go deep enough there might be repetitions, you do not take care of those repetitions in the message that is passed by some check node up on top, okay. You do not worry about that, okay. If you want to worry about all of that, then you will be optimal, yes, but then complexity is going to be huge, okay. So you give up there some optimality, that is why your decoders are suboptimal, but then the great gain is they work, and they work quite well, okay. They give you low BERs and FERs close to capacity, okay.
It was possible, will it touch capacity or will it
in the ML decoding? Yeah, I think so. Again, those are things that people are trying to prove. I think there are various versions, people have shown these results for LDPC and even turbo codes. They have shown that if you can do ML decoding or MAP decoding, you can get to capacity with these codes. So those things are again research problems that people have shown, so it is not totally unknown. There are papers, and such results you will not find in textbooks, because these are like ultra theoretical results. It involves a lot of combinatorial calculations. It is not very interesting otherwise. What is interesting in practice is the 10 power minus 3 FER that you can get. That is what is interesting. Okay.
Does that mean that any coding that you are doing, if you are able to do an ML decoding optimal thing, then it will reach capacity?
Okay, so then any coding such that finding low weight code words is hard. Okay, you can't do a very bad code. That's all. Just make sure that you are not doing anything that is very easily shown to be bad. Then if you do ML MAP decoding, the rule of thumb, the general folk theorem, so to speak, that nobody has shown but everybody believes in, is that you take a random code, random looking code. Of course, for random codes they have shown, but any design that you come up with, as long as finding low weight code words is hard, you do ML or MAP decoding, you will get to capacity. So these are all, I mean, it's not real theorems, but something that people use to guide design, and that's useful. Okay. Okay, so let me show you a few more ideas here. Turbo and LDPC codes are not the only ideas that follow these generic principles. There are other codes. Okay, the other codes that I will show you. The first thing I am going to show you is what is known as the turbo product code. Okay, product codes were always known, but this turbo product code is basically the turbo decoding of product codes. Okay, so let me talk about that for a while. It is called turbo product code. Okay, so it is TPCs for short. Okay, so the idea here is really interesting, and these codes have nice structure also, and they might be used some in some places. It's quite interesting to study them closely. Okay, so what is a product code? The product code is the following. Okay, so it has this. It has the structure. Your message, instead of being a one-dimensional vector, is now going to be. Okay, I am going to put 2 bars to indicate that it is a K1 cross K2 matrix. Okay, let us say a binary matrix. Okay, you can also do non-binary, but it is not too interesting. So the message is now a K1 by K2 binary matrix. This is the message. Okay, and then you take 2 codes. Okay, so the codes, there are 2 of them. One is a n1 comma k1 comma let us say d1 code with generator matrix G1. Okay, what will be the dimensions of the generator matrix? K1 cross N1. Okay, and then the other code, there are two of them, like I said. The first code is this guy. The second code is N2 comma K2 comma D2 with generator matrix G2, which will be K2 cross N2. Okay, so you have a matrix message. Okay, it does not matter whether it is a matrix or a vector, right. If K is large enough, you put it into a matrix form, it will become a matrix. It is not a big deal, it is just bits. You can think of it as a matrix or a vector or anything else you want. Okay, so we are not really deviating from the definition of codes just by going to 2 dimensions. Okay, but using these two codes is interesting, and how they form the code word is also interesting. You make a code word which is again a matrix. It is going to be an N1 cross N2 matrix. And how do you do that? You take G1 transpose, multiply with M, then you multiply with G2. Okay. So, okay, is this a valid multiplication? Everybody is happy. Okay, G1 transpose is going to be N1 by K1. M is K1 by K2 and G2 is K2 by N2, okay, and you will get a N1 by N2 matrix finally. Okay. So, you can now think of this is called the product construction. Okay. So, this is the product of the two codes. Okay. So, first of all, dimension and block length is easy, right. For the product code, what is the dimension? Block length is of course N1 N2, okay, dimension is K1 K2. The interesting question of course is what is the minimum distance. Okay. First of all, is this linear? You can show linearity quite easily, right. If you have a message M1, another message M2, what will happen to M1 plus M2? The same as C1 plus C2. Okay. So, you can show linearity very easily. So, clearly if this matrix, if you unwrap it and make it into a vector, you have a linear code, binary linear code, N1 N2 comma K1 K2 comma some minimum distance. The question is, what is this minimum distance? What do you think the answer will be? Okay, you have to think a little bit. Okay. So, remember, you can think of this, matrix multiplication is associative, right. So, you can pick any two first, multiply it and then multiply by the other. Okay. So, let us look at this multiplication. Okay. After you do this multiplication, okay, what happens to every row? Okay. So, that is this is a bad way of looking at it. Okay. So, let me do it slightly differently. Okay. Let us say we look at this product. Okay. So, we look at this two together, okay, and then what will this be? This will be a N1 cross K2 matrix, okay, right, N1 cross K2 matrix. I am multiplying this N1 cross K2 matrix by G2 on the right. Okay. So, after I do the multiplication, what will be each row of C? Each row of C will be a code word of the second code. Is that clear? So, each row of C finally will be a code word of the second code. Okay. Now, you can do the same thing, since matrix multiplication is associative, you can group that side and see it as a multiplication of G1 transpose on the left. That will show you that each column of C is a code word of the first code. Okay. Think about this carefully. If you have not seen it before, it is a little bit confusing. What am I doing first, what am I doing next, etc. Okay. So, it is quite easy to see. So, whether you do G1 transpose M first and then multiply by G2, or you do MG2 first and then multiply by G1 transpose, you should get the same answer. That is because matrix multiplication is associative. You can group it any which way you want, you will get the same answer, right. So, am I doing matrix multiplication here? Of course, I am doing matrix multiplication. Okay. So, you do the first two first, you get N1 cross K2 matrix, and then you multiply by G2 on the right. What is multiplication on the right? Each row you take and multiply on with G2, right, that is what you do. Okay. So, each row times G2 you are getting. So, ultimately every row of C belongs to the row space of G2. So, that will mean that every row of C is a code word of the second code, the code word generated by G2, code generated by G2. Okay. Now you do the same thing a little bit differently. Instead of thinking of this multiplication this way, you do the grouping this way, in which case you get what? K1 cross N2 matrix, right. And now you are multiplying by G1 transpose on the left, which means each column of this product Mg2 is multiplying the rows of G1, okay. And so you get every column of C becomes a member of the row space of G1 again, okay. So it is a bit of a twisted picture, you have to think about it. Yeah, you can do it in so many different ways if you like. I am not saying this is the only way to do it. Pull the transpose out so that you get the columns as rows, then you will see it as this thing transpose times G1, okay. That is probably a better way of seeing it if you want to see it that way also, okay. So basically the final result is that every row of C is the code word of first code, okay. It belongs to the first code, and every column of C belongs to the second code. Oh, okay. Oh, thank you very much. So row belongs to the second code and the column belongs to the first code. Is that okay? That is fine, right. So if I think of a non-zero code matrix C, right, in each row okay, there will be at least one row which will be non-zero, and that row should have at least D2 ones. Now look at those D2 columns, and each of them are non-zero code words of the first code, which means each of those columns should have at least D1 ones. So overall any non-zero code word of C will have at least D1 times D2 non-zeros ones, okay. So that is the idea, and coming up with the code word minimum distance. So you can have a lower bound on the minimum distance, this is at least D1 D2, okay, right. So that is the product code. Like I said, the product code was known for a long time, it was not an unknown code, okay. But notice from a modern point of view, this is nice except for the randomness, okay. So G1 and G2 are like fixed codes, maybe you can live with that, it is not random, but then the decomposition that it gives you is very obvious, okay. What is the decomposition? Every row belongs to the second code, every column belongs to the first code. So if you were to come up with a decoder using the modern principles of message passing decoding, what would you do? Okay, what can you do? What are your component decoders?
You look at it as rows and columns.
So one thing you can do is you have a decoder for the second code. Maybe you have an optimal decoder for the second code. Then what will you do? First you decode all the rows, okay. So after you transmit, you receive the received values, you put them in a matrix, okay, and then you decode all the rows using your optimal decoder for the second code. Now you have to gather some extrinsic information and give to the another decoder, which is the column decoder, okay. Column decoder is an optimal decoder for the first code, okay. So how you do the extrinsic is not quite clear here, okay. It is a little bit more confusing. In fact, when people do it, they just do a scaled down version, just multiply it by some 0.7 to reduce the positive feedback, so to speak, just control something and then you give it to the second decoder, and the second decoder works on this, decodes all the columns, okay, and then the first decoder takes over, okay. So you go back and forth like this, you hope to improve your performance, okay. So this is another idea. Is that okay? So once again, the only thing that is kind of missing here is the interleaver and all that. So it is very common to pick G1 and G2 to be generators of Hamming codes or extended Hamming codes. So you would take the 1611 is particularly common, okay. So you take the 1611 Hamming code, okay, take its generator matrix, and then Hamming codes you can easily decode, okay. You can also do soft decoding without too much effort for Hamming codes, so you can do that, okay. In fact, there are also suboptimal soft decoders possible, etc., etc. So all these things that people use in the turbo product code construction, okay. So this is one idea. In fact, there are other ideas, many other modifications to this, which I will skip. And then the next set of codes are what are called repeat accumulate codes. And these are particularly simple. Again, I think to me these codes represent the real power of this modern approach, okay, repeat accumulate codes or RA codes. Okay, the encoder is so simple, and the decoder is once again uses these iterative ideas. So you will see it's kind of a demonstration for this modern idea, how well does this modern idea work. Okay. So repeat accumulate, okay, so that's the word, I mean that's what indicates this code. So what are you going to do to your message? You are going to repeat your message bits, which is a repetition code, which you know is not very good, and then you are also going to accumulate, okay, and then using our modern ideas, between the repetition and the accumulate we are going to put some random permutation, okay, and that's it, that's all you do. Okay, what do? You have a message M, okay, it goes through first a repetition code, let us say a 3, 1, okay, so let me just do, it is very common to do 3 repetitions. So I will say repeat each bit 3 times, okay, so each bit is repeated 3 times, okay, so this is bitwise, okay, when I say repeat thrice the message itself is repeated 3 times, okay, so you get a code word here, so maybe let us do M, okay, or some permutation of it, you might do M1, 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 M2, 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 something, one of these things, I think it's something, does not matter, and then you have a permutation, okay, and this is going to be a random permutation, okay, and then in fact what you do is this accumulate. What is an accumulator? Accumulator is basically something which does 1 by 1 plus d, okay, right. What is 1 by 1 plus d? Okay, if xn is the input, yn is the output, what will be 1 by 1 plus d? Yeah, so yn is going to be summation of xn xi, okay, so let me do it carefully, xi I equals let us say 0 to n, right. So it accumulates, this 1 by 1 plus d is shorthand notation, I think all of you must know this, you have done enough DSP to know this. So this is the accumulator, that is it, that is your code, okay, this is the repeat accumulate code. So there is also a systematic version where your message will also come through by itself, okay, so this can be the parity and this is the message. There is also a non-systematic way where you do not send the message explicitly out, you only send the parity, okay, so there are various ways of doing it. Okay, once again 2 codes which are very easy to decode, optimally decode, the repetition code can be very easily optimally decoded, there is no problem there, you know the complete exact decoders. 1 by 1 plus d is a very simple trellis, okay, so it is a 2-state trellis, okay, how will the trellis look? It is very easy to come up with a trellis, 1 by 1 plus d, it will look like this, okay, so you can write down, we will come to all that slowly, okay. So it is a trellis that looks like this, you can put the transitions, 1 by 1 plus d is just a 2-state trellis, so you can do BCJR very easily. So you have optimal soft decoders for both these things, so you can construct a turbo decoder, right, you do a first you decode the 1 by 1 plus d, you get some extrinsic information, you do the permutation, you send it to the repetition encoder decoder, which again does some more improvement of your LLRs, then you go back and forth, you can keep doing it, okay. So a very standard turbo decoder can be constructed, okay, yes.
Does it add some extra redundancy which the repetition didn't have?
No, it does not add any redundancy, accumulator is a rate 1 kind of thing.
Yeah, so why do we do that?
Well, it does something, you know, it gives you a trellis on which you can decode. So I want to point out, that is what I want to point out here, right. So that is, for instance, the question he asked is very interesting, because 1 by 1 plus d is not doing anything, I mean rate is 1, right, whatever you put in you are getting out, okay. So but what it gives you is some way of getting soft information and it adds a certain other dimension in the dependency, okay. So you have repetition which is very local, you know, everything is repeated, and this accumulation somehow connects everything together. So you are able to pass your soft information all around, you know, it goes through and slowly trickles down from here and there, it is like economics, ultimately the poorest guy also benefits, okay, that is the idea, okay, and nobody knows exactly how, but there is a random permutation in the middle, doing its magic also. So it works, and that shows you the way these modern codes work. I mean, just don't pay attention to the actual code, pay attention to your decoder. Make sure that you can't come up with a very simple low weight code word. Okay, so here also even here coming up with a low weight code word is a little bit non-trivial, but it's not too hard. You can come up with a low weight code word. Can you? How will you come up with a low weight code word here?
If you know the random permutation, then you can come.
Okay, let's say you know the random permutation.
What is the last thing? One. Oh, you need thrice.
You can't do that. See, the accumulator is going to make any weight 1. See, if you put just a 1, it's an IIR filter, right? It's going to put a lot of 1s out. So you have to be careful, right? So it's a little bit tricky, right? You have to do it. You might be able to get there. Okay, given the random permutation, it's not too difficult. I'm not saying it's difficult, but it's not obvious. It's not obvious that it's plenty also. You can't just come up with low weight code words very easily. Okay, so that follows that principle, and the turbo decoder can be constructed. In fact, what you can also do is you can construct a graph, okay, and do message passing also. Okay, so you can construct a graph and do message passing. Okay, so I haven't spoken about this in the class, but it's kind of interesting to think about how you might want to do it, but it's something I want to point out here. So do message passing, this is basically like the LDPC decoder. So without BCJR, that's what I'm saying. So one way is to do BCJR, another way is you can even do you can construct a graph. It's easy in this case. I'm not doing it explicitly here. You can construct a graph and then do local message passing kind of thing, and then that also gives you good performance for the repeat accumulate code. Okay, and there are all kinds of variations here. Okay, so this is repeating everything thrice. You might want to repeat some things more than the others. Okay, that's called irregular repeat accumulate. Okay, so you might want to do that. So what is the distribution with which you do that? Which ones do you get repeat twice? How many do you repeat twice? How many do you repeat thrice? How many? So you can optimize over that and optimize that and get good irregular repeat accumulate codes. So all these things can be tried. I mean, all these variations will give you better and better things. In fact, I believe people have shown that these codes can achieve capacity on this binary erasure channel and all that. Even in AWGN, maybe they get close to capacity. Okay, I'm not very sure, but on AWGN, but on erasure channel, I believe people have shown that this construction achieves capacity. If I'm not wrong, I think I have to recollect this. But anyway, so there are some optimality results, capacity approaching results that people have shown for these codes.
The original repetition could also pass through the accumulator again, or because it's only the permutation which we are sending through the accumulator.
What do you mean permutation is sending through? Bits are going through the accumulator. Permutation does not go through.
One accumulator thing. So where does the turbo decoding come into it?
No, the repetition code also will do. I mean, you'll have a block which decodes the repetition code. That will not be a BCJR, but it will be something simple. But
okay,
it will be another block.
So it need not have to be 2 BCJs for a turbo decoder.
No, definitely not. You can use the turbo principle. So you will have one decoder which decodes the repetition code and gives out soft output. You have to figure out how to use extrinsic input in the repetition code, and that's very trivial. You can just do that without any problems. So you figure that out, and then you have extrinsic input, subtract it out, send the extrinsic output. That's what I mean when I say turbo decoder. Use the turbo principle in the decoding. Okay, so you have one BCJR, the other will not be a BCJR, something else, but then you use the extrinsic subtraction principle and then you do it. The reason I called it turbo is it's more or less like a one-shot decoding. I mean, using the trellis once, and then you're coming back here and going back. So that's the idea. So you can also do something else. That's why I said you can construct a graph and do message passing, and that also works quite well here. Okay. So I think in this class we've seen both the traditional codes, okay, which culminated in the Reed-Solomon codes, and in fact convolutional codes are also traditional codes. Okay, and there are interesting differences between the traditional approach and these modern approaches. Okay, one thing that these modern approaches do not have is a clear characterization of minimum distance. Okay, it's only a rough characterization, but the advantage that they have is they allow for suboptimal soft decoding, which works very well. Okay, so the holy grail, so to speak, is to have a perfect union between the two. Right, so you come up with a construction which has guaranteed minimum distance, okay, which also in a way grows with block length. Okay, when you increase block length in your construction, the minimum distance has to grow maybe linearly, maybe sub polynomial, I mean sublinear polynomial like n power 0.2 or n power 0.5 or something, root n or something like that, just to grow with n, it cannot be log n, it cannot go to log. Once it goes to log, it turns out whatever you do with the decoding will get killed. Okay. So just to grow with n, can you have that? If you can have that, then you should still be able to do optimal soft decoding. Okay, you should, and that construction should not be like some very arbitrary random construction where you can't do soft decoding. If you can do soft decoding also, and if you also can show minimum distance, then you have made a union of the two, then you have a nice new code for which you might get awards for those. Okay. So those are interesting problems today. Okay. So let us leave this here, and we have about 20 minutes. The last item that I want to talk about is higher order modulations. We have been always talking about BPSK, and what do you do if you have 16 QAM, 64 QAM, and these are being used today increasingly in many communication systems, and you should know how the architecture looks. Okay. So the typical way of doing this is basically, okay, so the title is coded modulation. Okay. So when you say coded modulation, well, BPSK is also a modulation, but people do not consider BPSK as coded modulation, they will say it's obvious. So when you say coded modulation, it is implicit that you are going to at least 16 QAM or something like that, no, some 8 symbols must be there in your modulation alphabet, only then it becomes non-trivial. Okay, otherwise it is very trivial. Okay. So there are several things here. The first thing is, if you look at 16 QAM, okay, you are going to have let us say the regular QAM, okay. So basically this will be 1 plus or minus 1 plus or minus j, and then plus or minus 3 plus or minus 3j. Okay. This is 16 QAM. So the first thing is that you have to worry about is bit to symbol mapping. Okay. So how many different ways can you map symbols to bits here?
Must be new, so 16 factorial.
16 factorial. So it's a huge number, so you're not going to exhaust all of them. So that you have to use some thumb rules to design something that's nice. One of the most common things that is used is what's called gray mapping. Gray, GREY or AY? EY. Okay. So gray mapping. So here you make sure that adjacent symbols differ only in one bit. Okay. So you can come up with a mapping like that for this. So that's most common. You can also use other mappings. Nothing stops you from doing that, but you have to show that the other mapping that you're using is better than gray mapping. Usually it's hard. So let's say we fix gray mapping. It's not a bad deal. And I don't know, can anyone come up with a gray mapping very quick? You know how to do that? So you know how to do that, right? So you can do that. So you can put for 4 at a time, and then you add the remaining to 4 in this particular direction. It can be done very easily. Okay, so you can come up with a gray mapping. Okay, so now how do you use this with the code? Okay, so what is done usually is, okay, this is what's usually done today. Okay, so in many standards people do this. Okay, you have an outer code, let's say an LDPC code. Okay, you can also have a turbo code. Okay, basically not an outer code, you have an LDPC code. Then what people would do is, you might want to do a permutation here. Okay, so I'll tell you why this permutation might be needed. You might want to do it, may not want to do it. There are some reasons why the permutation might be needed. Okay, and then after that you put it into your gray mapping for 16 QAM. Okay, so this is how your encoder looks. Okay. And then noise gets added. Now you will have 2D noise, right? You're putting out complex valued symbols. You will have complex Gaussian distributions. Let's say 2-dimensional independent normal distribution, each of them with some sigma squared, and adds up to some 2 sigma squared, etc. So you will get complex valued things. Okay. So basically you will get 2D real values here. Okay. So your received vector will be basically r equals r1, r2, so on till rn, and each ri will be xi plus j yi. Okay. All right. So now what you need to do is come up with what is called a 16 QAM demapper, okay, and this demapper has to be a soft output demapper. Okay, what you need here, see here you have bits, right, here you need LLRs for bits, that is it. Okay. Once you have LLRs for bits, it does not matter what modulation you are doing, okay. You can easily separate the modulation part of things with the coding part of things, okay, because what is input to the LDPC code is LLR, what is input to the turbo code, it is kind of like LLR, right. So, LLR is what you input into the thing, but you think there might be like branch metric that you have to compute. So, there is a way to incorporate that in the turbo code. So, that is why I did not go into the turbo code stuff, but usually LDPC codes it is quite straightforward to see what you have to do. The LLRs can also be converted into the branch metrics in turbo codes, it is not too hard, okay. So, what you imagine sometimes is that these LLRs are actually coming from a BPSK modulation, even though it actually went through 16 QAM and came back, because you are doing this permutation and it is all looking random. So, what people usually assume is that what comes out here is LLRs. So, you assume that it is approximately from BPSK, okay, pi inverse, okay, everybody is, maybe pi was such that pi squared was 1.
Actually scalar LLR.
Yeah, these will be scalar LLRs, okay. So, this will be scalar, this is all scalar LLRs, okay. So, I will do a quick discussion on how to compute that scalar LLR, it is quite easy, okay. When I say scalar, what I mean is each symbol here has 4 bits, right, B1, B2, B3, B4, okay. So, this scalar LLR will be, what will this be? This will basically be, if you look at the ith bit, okay, log probability that BI, no, BL equals, no, B, let me do the symbol carefully, okay. Let us say BIL equals 0 given RL, okay, divided by probability that BIL equals 1 given RL, okay. So, that is what I mean. So, it is given only that L, no, RI, right, sorry. Okay. So, L will go from, L is 1, 2, 3, 4, okay. So, what you do is once you get these LLRs, you think of them as roughly coming from BPSK, you do not worry about the modulation after that, okay. I have got my LLRs, think of it as 2 by sigma square into something, you know, you assume that is what has happened and then you decode, okay. So, in fact, most decoders, like I said, are either min sum or max log map, okay, they do not need the sigma squared. So, they only need some number which tells you a certain confidence about your bit, okay. If that number is large, it means large and positive, it means that bit was 0, okay. If it is large and negative, it means the bit was 1, okay. That is all you need, okay. And then inside the decoder you use it and then you can improve your iterations, okay. So, this is the typical way, particularly if you do gray mapping, this is more than good enough, okay. You can simply treat it as like BPSK, because when adjacent symbols are vary only in 1 bit and you do not have to worry about things far away, everything depends only on what is next to you and then you get a BPSK kind of situation, okay. So, this is a common approach, okay. Once you get the scalar LLRs, you treat it like it is from BPSK and then run your decoder just like before, okay. So, the only non-trivial step is to compute this demapping scalar LLR, okay. How will you go about computing it? You have to use Bayes rule. So, let me show you how that is done, okay. So, probability that BIL equals 0 given RL, it is going to be RI, okay, thank you. It is going to be f of RI given BIL equals 0 times probability that BIL equals 0 divided by f of RI, is that right, okay. Now, when I am going to divide and take ratios etc., what is going to happen? This is going to go away, this is going to go away, okay. I do not have to worry about these things. The only thing I have to worry about is f of RI given BIL equals 0, okay. How do I compute this? F of RI given BIL equals 0, okay. So, you go back and look at your constellation, given that BIL, I is quite irrelevant, right, for every I you do the same thing. Okay. So, given that say B1 is 0, how many points are possible in this constellation? 8 points, right. So, that is totally 16 points, you fix any one bit there will be 8 different points. Okay. So, given only that B1 is 0, you will actually have a 2-dimensional mixture Gaussian with 8 different Gaussians adding up. Okay. So, that will be the distribution. So, you plug in the received value into that distribution, you get the answer. Okay. So, once you find the PDF, what is this PDF? This PDF is going to be summation, okay, let us say 1 by 8. In fact, this 1 by 8 is quite irrelevant, because when you divide it is also going to go away, normal with mean, suitable mean, and then some variance. This will be a 2D normal. Okay, 2D normal distribution, this is what it will be. Okay. So, you know exactly what the formula is, you plug it into the formula, you are going to get the value, that is it. Okay. For BPSK it is very simple, because there is only one Gaussian. Okay. Actually it will be a Gaussian, here you have multiple Gaussians, shifted means adding up together, it is just a more messy expression, but theoretically it is nothing. And this 1 by 8 you do not have to worry about, because anyway when you do LLR in the denominator also it will come and it will cancel. Okay. So, ultimately the scalar LLR will look like log sum of Gaussians by sum of Gaussians. Okay. Right. So, what is Gaussian now? So, e power something, right. So, log of e power x plus e power y plus e power z, so on. Okay. Again you can use your max log map approximation. Okay. Whenever you have log of e power x plus e power y, if x is greater than y, it is going to be much closer to x than y. Okay. So, e power x is an exponential function, if x is greater, e power x is going to be much larger than e power y, you can kind of approximate it and drop it. Okay. So, you do that, and that is also very commonly done in practice and implementations. Okay. People will simply look at the, in fact they will look at the received value and see the closest point in the constellation with the particular bit being 0. Okay. You look at that distance, you simply use that distance instead of the numerator. Okay. And then from that you subtract the other distance, closest point where that bit is 1. That is what most people do in practice. That is the max log map approximation to this expression. Okay. But you can also do the exact expression, it is not a big deal. Okay. You do that, you get your answer. Okay. So, this is not too much detail, but that is what is done. Okay. So, in fact you can imagine in gray mapping this is not so, what I am going to say next is not so useful, but if you have other mappings, this structure is reminiscent of what you can do in turbo, right. Remember the 16QAM, of course it does not have any redundancy, but it gives you a way of computing scalar LLR, some soft output it is you are able to compute. In fact you can use the priors. Okay. So, here I have set the priors to cancel out, but if you are getting some extrinsic you can use that in the priors here. Okay. So, in fact in some mappings, in gray mapping it is not very good, but in some other mapping you have to do iterations between your LDPC decoder and the demapper to get best performance. Okay. So, you get the demapper out assuming equal distribution for all the other bits, come to the LDPC code, it gives you some information, you pass extrinsic back to demapper, use that as extrinsic input right here. Okay. So, you are going to use it in extrinsic input here. Okay. And then you go back to the LDPC code and you can do iterations, and that will give you some improvement if you are not doing gray mapping. It turns out in gray mapping one can show the gains are very minimal if you do iterations, so people do not do it. Okay. But in non-gray it can give you good performance. But gray mapping is usually the best, it gives you pretty good FER and BER, so people settle for that. Okay. So that is so this for instance is called BICM, okay, block interleaved coded modulation, okay, and this is commonly used. In fact, if your LDPC code does not have a regular structure in degrees and all that, people do not even do the permutation. But if your degree structure for LDPC codes is in a sequence, It is good to do interleaving to mix it up a little bit. Okay, so we are down to the last 5 minutes of the course. Okay, so in the last 5 minutes, I am going to talk a little bit more. Everybody's, why doesn't he stop now? I can hear you. Don't worry about it. Okay, the only thing I am going to say is a few things which are of interest, very recent ideas which we will not have time to discuss in detail, but some things that I think are interesting and new ideas. One idea called polar codes is very interesting. Okay, so these are, in my opinion, some kind of a union of traditional and modern ideas. Okay, so you have good minimum distance will be roughly like root n or something. It is based on what is called a Reed-Muller code. It is an interesting construction, and the decoding is quite modern. Okay, and these, for instance, you can show explicitly that they will approach capacity. Okay, for LDPC and other codes, it is difficult to show that. It is big painful to show those things. These codes under very implementable decoders will achieve capacity. You can show that they achieve capacity. Any rate below capacity is achievable. Okay, so it's they are very good. These are being studied very actively today in research. Polar codes is something we didn't have time to look at, but it's an interesting idea. Another way in which coding is progressing is basically, so today many people think that the point to point coding problem is reasonably well solved, understood and done, so to speak. Okay, point to point, what is point to point communication? You have one transmitter, one receiver. Okay, one transmitter to one receiver. Okay, of course, now what's non-trivial today is network communication, right? So, and almost all communication that you do today is networked. Okay, cellular network is an example, wireless networks around on campus is example, and many communications are network communication. So, in network communication there are quite a few non-trivial coding problems. Okay, you do not have to go so far as the cellular network and look at very complicated scenarios. You can look at very simple scenarios, like for instance one transmitter talking to two receivers. Okay. Okay, so problems like this are called multi-terminal problems or network problems. Okay, so doing codes for these kind of problems is a little bit more complicated. Okay, this is also another direction in which codes are evolving today. Okay, so another interesting challenge is problems like this. This is the simplest example, but of course there are more complicated examples, something called the interference channel, which is a little bit more similar to the cell phone network, etc. Okay, this is another interesting direction in which you can move. Okay, so in point to point communication, what is left is making a perfect union of this traditional and modern ideas. Okay, once you come up with a nice code which has good minimum distance, for which you can provably show that it achieves capacity, pretty much the point to point problem will end. Okay, only problems that are left are things like wireless, where you don't know the channel ahead of time, and so some complications in that direction are still left. Maybe ISI is still a little bit more open. Okay, but mostly point to point communication people know what to do. Okay, one transmitter, one receiver. When you have network communication like 3 transmitters, 3 receivers, and they are all interfering and each of them wants to talk to each other, okay, that is called an interference network. It is being hotly studied today. Okay, how to do coding, how to do, in fact how to even approach coding is not very well known. Okay, so people are looking at that also. Okay, so these are just one slide in the last 5 minutes about what might come in the future. Okay, so that's it. That's the end of the course.